Hi there, everybody. This is Malcolm KCP coming at you pre-recorded. So we are going to be starting off with a little bit of a review / covering the second half of our last lesson, because I know we didn't get fully to it, and then we're going to jump into the next lesson, and I'll probably do a separate video for the additional lesson that we're missing because of this COVID scare. Just to start things off, quick set of definitions here. We are going to be talking about exponential functions. So exponential functions are any function that has the form where the y value is equal to some constant times another constant raised to a variable power. So here we would interpret this a is just multiplied in once, but the b is being raised to some power. That power is equal to the x value. So an example here would be f of x equals 3 times 2 to the x power. A graph like that would look something like this. 3 times 2 to the 0 powers. 2 to the 0 power is 1, so we'd just get 3 times 1. So we'd have a point here at 0, 3. But then every time the x value increases by 1, that means that the power of this 2 is increasing by 1, right? So when x is 1, we're going to have 3 times 2 to the 1, which would be 6. This point would be 1, 6. Then we would have 3 times 2 squared, or 3 times 4, so that's going to be 12 up here. So we'd have 2 comma 12. I can get this out of the way for us. And in general, every time I move 1 unit to the right, because this b value here is 2, the base that's being raised to the x power is 2, that means I'm going to be, every time I move 1 unit to the right, it's like I'm doubling the y value. So you can see this is going to go really, really high really quickly. And similarly, every time the x value decreases by 1, it's like going to be like I'm cutting this y value in half, right? Because, for example, 2 to the negative 1 power is 1 half. So you'd have 3 times a half, or like 1.5 down here. Then down here you'd have 3 times a quarter, or 3 quarters. You'd have 3 times an eighth, and so on. So as we go to the left, we're never going to quite reach 0, because we're just multiplying 3 by fractions, but we're going to get closer and closer every time. And so this is the general shape that exponential functions all have. Notice I kept talking about 2 and 1/2. That's because that b value, that base value there, is 2. If, for example, that was a 5 there, like 3 times 5 to the x, then every time I move to the right, my y value would multiply by 5, and every time I move to the left, it would divide by 5. Notice that here we have a domain from negative infinity to positive infinity, because you can raise a number to any real number to power, right? You can raise numbers to the 0 power, you can raise numbers to negative powers, that gives you a fraction. And so there's no x value I can plug in that will cause an exponential like this to have any problems in its domain. Its range is either going to be from 0 to infinity or from negative infinity to 0, depending on whether a is positive or negative. So our range is going to be 0 to infinity, not including 0, if a is positive, and it's going to be negative infinity to 0 if a is negative. If a equals 0, then the whole function equals 0, right? Because it would just be 0 times b to the x, and so we wouldn't really consider it an exponential if a equals 0. So we don't worry about that. But I'm going to, again, give you the general rule here. When x increases by 1, f of x gets multiplied by b. So again, if you look here, when we start out here at x equals 0, and we have this 3 here, which is our a value, moving 1 unit to the right on my graph means that I'm increasing this x from a 0 to a 1, so I get 3 times 2, so that doubles my y value, right? 3 times my b value here is going to be 6. Here, if I move 1 unit to the right again, I'm going to multiply by my b value of 2 again, and so my 6 will turn into a 12. Likewise, as I move from right to left, I'm dividing by 2 for my y value every step of the way, right? And so this is like half of what it was before, this is half of the one before that, and so on. So that's the general idea of how this is going to work. There are some, obviously, ways that your function could look a little different. For example, here is like, if I say g of x equals negative 7 times 10 to the x, then instead of having that range from 0 to infinity, because our first term here is negative, we're going to have like our first point is going to be down here at 0, negative 7. Forgive me for the scale of this graph. That's a 7, not a 1 there. It's a negative 7. And then as I move to the right, I'm going to multiply by 10 every time. So I'll suddenly have a point down here at negative 70, and then the next point will be down even further off the graph at negative 100, and so like if I zoom it way out, the graph will end up looking something like this, right? Where instead of pointing upwards, because we have this minus in front of the whole thing, we get a vertical reflection and it points downwards. Notice that every single exponential has the point 0, comma a on it. So when I say 0a, I mean 0, and then is the x value, and then the number that's in front, that's not the base, but that's just being multiplied by the base, that's going to be your y value. So if that number isn't there, which we would say a is 1, then you'll have the point 0, 1. So for example, the function f of x, or I'll say h of x here, function h of x equals, let's say, pi to the x, which is an exponential function because pi is just a number. By the way, a part of this definition here is that a and b are just both any real number. Technically speaking, you'll almost always see b b will be positive. A doesn't have to be positive though. And so since pi is a real number, this is an exponential. It's going to look just like these other ones. So it's going to have this point here at 0, 1, right? Because there's no a term. You can think of this as like 1 times pi to the x. And then over here, it'll have a point at like 1 pi, 2 pi squared, 3 pi cubed, etc., right? So just understanding that, let's switch over very quickly to our worksheet. We're going to talk about problem 3. I highly recommend, by the way, I'm going to post the worksheets alongside these videos. I recommend that you have them with you and work on them, whether you're just looking at them and working on scrap paper or whether you are able to print them out. Don't just watch this video. That's not how to learn actively. You want to be participating, right? You can even start trying the problems a moment before I go through them. You can always pause the video. And then as soon as you come up against something that you don't know how to do, that's when you can unpause the video and see what to do here. So in general, this is just kind of, this could be calculator work or better yet, work by hand. All we're doing here for 3a and 3b is plugging in values for x and evaluating the function's y value, right? So here they say f of x equals 2 times 3 to the x, and that x equals 3. So you can pause your video and complete this if you like. I'm going to move forward. So here we have f of x equals, I can go back to black here. F of x equals 2 times 3 to the 3 power. Usually I plug in parentheses. In this case, it's not really that important to plug in parentheses. Now, order of operations reminds us that exponents happen before multiplication, right? PEMDAS, parentheses, exponents, parentheses, exponents, multiplication and division, and addition and subtraction. Keep in mind those are like in the same step. So here, the first thing we do is raise 3 to the third power, which gives us 3 times 3 times 3, or 27. And then we do 2 times 27 and get 54. So we would know that on this function, on the graph of this function, we would have the point. So first of all, we could say f of 3 equals 54, which means that on the graph of f of x here, we would have the point 3 comma 54. But they just asked us to evaluate f of x, so this number would be fine, or saying f of 3 equals 54 would be fine as an answer. This next one here looks a little scarier. This is actually technically not an exponential based on the definition I just gave you. It's more like a transformation of an exponential. This is an exponential where the x value is being messed with first, so that's a horizontal shift. This is being translated horizontally to the right 3 units. But it doesn't matter, we can still plug in 1 just fine. So here we have f of 1 equals 5 times 2 to the 1 minus 3. Now, order of operations, you might think to try and evaluate 2 to the 1 minus 3 first, but think of this like a set of parentheses in here. You should evaluate what 1 minus 3 is first. So this is 5 times 2 to the negative 2 power. Here is a reminder about how negative exponents work. Negative exponents do not make positive numbers turn negative. If I ever see you say that like 5 to the negative 2 is negative 25, I will be very disappointed. Negative exponents are division by the positive exponent. So this is like the same thing as saying 5 times 1 over 2 squared, aka 5 times 1/4, which we can just write as 5/4. So our final answer here would be that f of 1 is 5/4. This is just calculation. I encourage you, if any of this is confusing, that means you need to practice order of operations with exponents. So please do that. Do not, if you ever come across anything in my class that confuses you, you need to A, come to me with questions immediately, and B, look that content up on your own as well, because you can't learn passively in this class. I've been grading the tests, and there is some big mistakes on things that are like prerequisite knowledge for this class, so please make sure that you are practicing any skills that seem to be necessary to solve problems but that I'm not teaching. That might mean that that's a skill that you're expected to already have coming into the class. And evaluating expressions like this is one of those skills. So, now let's talk about problem 4. They want us to find an exponential function that passes through the points 2, 3, and 4, 27. This is very similar to problems like find a line that passes between 2 points, right? You have to use the fact that the points are on the graph as well as any other information you know about that particular kind of function. Now, if we were looking for a line that passes between these points, one way we could do this is to write down the standard form of a line. Again, this isn't how this problem works, but we're going to imagine for a moment that we're solving this problem for a line. If it was a line, we would write down the standard form, or in this case, the easiest form to work with, which could be point slope or slope intercept, right? I'll say point slope. We would write down y equals, or not point slope, slope intercept, which is my favorite one to work with, right? Y equals mx plus b. Then we'd have to think, okay, well, y and x are just variables, but m and b are numbers that we need to know, right? So we need to find this, and we need to find this. So we can find this by using our slope formula, and once we have this, we can plug in x, y, and m and solve for b, the y-intercept, right? Now, this isn't a line, so we won't be doing that, but we'll be doing something remarkably similar. I'll leave this off to the side. So our conclusion there was that we needed to find m and b. But it's not a line, so instead we're going to write down the standard form equation I just gave you for an exponential, which is f of x equals a times b to the x. Now, f of x and x are just our input and output variable, right? So what we need to do, of course, is find, got colors here, I might as well use them. Find a and b. Now, because we're new to working with exponentials, this might be a little bit daunting, but there are tricks we can use. If you look back at or let me just say this. If the point 2, 3 is on our graph, that means when I plug in 2 for x, I should get 3 for f of x. So what I can do here is say, all right, I know that if I were to do a times, or I'll stop the green here, that's just a mark, some important information. If I know, so basically 3 should be equal to a times b to the 2 power. That's what I've just done here. So here I just plugged in 2 for x and 3 for f of x, right? F of x being similar to our y variable here. Now, does that help me? Not exactly yet, but what if I did it with the other point too? And 27 equals a times b to the 4th power. Now, here's a neat little trick. Because we know that 3 equals a times b to the 2nd power, and 27 equals a times b to the 4th power, what we can do is, so 27 divided by 3 must equal a times b to the 4th over a times b squared, meaning 27 over 3 must equal b squared, right? Because that cancels out all to b squared. 27 over 3 is 9. And so we know 9 equals b squared. I told you before b is always a positive number. So b must be 3. And if b is 3, which the other logical way to think about this is, I told you before, anytime x increases by 1, we multiply our y value by b, right? So here, to get from this first point to this second point, x increased by 2. So that means we must have multiplied by b squared, right? We multiply by b 2 times, not 2b, but b squared. And so that means that 3 times b squared equals 27, which you could also solve and find out that b equals plus or minus 3. And again, in this case, we'll assume that b is always a positive number, so b equals 3. Now that we know b equals 3, it's pretty easy to go back into either of these 2 points over here and use that information to solve for a. So that's sort of the last thing, but I'll say since b equals 3 and 3 equals a times b squared, we can do 3 equals a times b squared, which is 3 equals a times 3 squared, because b is 3, which means 3 equals 9 times a. When we divide both sides by 9, we get 1/3 equals a. So our final answer here is f of x equals a is 1/3 times b is 3 to the x. 1/3 times 3 to the x. is our final answer. Again, just to walk through what we did here, we used the points 2, 3, and 4, 27, and we used the standard form equation f of x equals a times b to the x to learn that 3 must be a times b squared and 27 must be a times b to the fourth. That means if we divide them, 27 divided by 3, right, the higher x value divided by the lower x value, we're going to get just b squared, because the a's over here are going to cancel, and then this b to the fourth over b squared will give us b squared. So that means 27 over 3, which is 9, must equal b squared. Square root both sides, and remember that b is always going to be a positive number. That was part of our definition over here. B is positive. And you know that b has to equal positive 3. And once you know b is positive 3, plugging that fact into either this or this, either one of the standard form equation with our point plugged in, is going to give us a way to solve for a being 1/3. And you can double check your work at the end. Remember, you should always double check your work on these problems by plugging in 2 to this equation that you gave as your answer and seeing if you in fact get 3 as the answer. Here I'll get 1/3 times 3 squared. So that's 1/3 times 9, and 1/3 of 9 is indeed 3, which is the y value that we're supposed to get, so that works. And you can do the same thing with the other point. So 1/3 times 3 to the fourth, I happen to know 3 to the fourth is 81. 81 divided by 3 is indeed 27, so both points work on our function. Our function is in a times b to the x form, and both the points are on it. That is all they asked us for in this problem, so we must be done. Not enough checking of work on the exam. Y'all need to be checking your work. Some nonsensical answers on those exams. All right, so now we have to talk about a new definition, which is interest. So we've got our exponential formulas here. Let me see if I can just change my canvas size here to be a whole lot bigger. We'll just go with percent, and I'm going to make it 500% bigger in all directions. There we go. Sorry, it's my first time not using Zoom to do screen recording. Hope this is working out well. So here we have a new definition that we need. We're going to be talking about money. Specifically, we will be talking about a set of exponential equations that happen to be very important mathematically, known as the interest equations. So we have two interest equations. We have the compound interest equation, or interest formula. And then we're going to have something over here which is much more mysterious, which I will call the continuous or continuously compounded interest formula. Now I'm going to be real with y'all. Part of the reason that we talk about this is capitalism. Part of the reason that we talk about this is that a mathematician discovered a really important number, which we now call E. It's an irrational number. It's approximately 2.71, but just like pi, it has an infinite non-repeating decimal expansion, so we just give it a name so that we don't have to write it exactly. A mathematician discovered this number while studying interest, and then that number turned out to be wildly important for all sorts of other areas of mathematics. If you look up the discovery of E online, there are some great videos on that, so I'm not going to waste your time going through that discovery right now, but I highly recommend you do so because it's very interesting. But for now, what we're going to do is focus on learning these two formulas. They're both going to seem super scary at first. Honestly, the continuous one is nicer, but bear with me for just a moment while I give you these definitions. All right, so the compound interest formula. is usually written as A equals P times 1 plus little r over little n to the power of nt. Now, what the heck does any of this mean? So, A here, which usually stands for accumulated amount, is essentially the final amount of money. We're assuming this formula applies to when you put money into a bank account and it gains interest over time. So we use this formula to determine how much money will be in your bank account after T years if its interest rate is R and you deposited P. Again, I'll give all these definitions. So A is the final amount. P, or the principal, again, that's just a standard word for it, which you might need to know to see it on Lumen and stuff, is the original amount. So this is how much you deposited into the account when it started. Again, we're dealing with money here. So this is usually, these are both in dollars or whatever currency you're working in. R is really important. R is the annual, that means yearly, interest rate. As a decimal, but it's usually, like, if you say, for example, that R, your interest rate, is 7%, that means that R is actually going to be written as 0.07, right? 7/100ths. Because percents are just fractions out of 100. N, here, N is the number of times interest is compounded, which here just means added, per year. So for example, if they say it's compounded monthly, that means N is 12. If they say it's compounded, for example, quarterly, then N is 4. If they say it's compounded yearly or annually, then N is 1. They could say it's compounded daily in this class. If they say daily, assume 365. Don't do any funny things with leap years or the fact that a year really has an extra quarter of a day in it. Assume daily means 365. I think weekly would be 52, but I don't think I've ever seen this course pull up a weekly for you. So N is really important here because if you look here, we're dividing the rate. I'll write the last variable here, and then we'll talk about what this all means. Finally, T is the time in years. So the unit of time is always years here. It's really important because R is the annual interest rate. If T were to represent time in months, for example, then you would need R to be some sort of a monthly interest rate, and N would have to be like the number of times per month interest was compounded. I've almost never seen them require you to do that kind of thinking on this, though, so just assume T is in years, R is an annual interest rate, and N is the number of times per year. So again, this formula looks a little scary to start with. Let's jump into where it comes from. The big idea of this formula is that this whole thing right here that I've just circled in purple is a percent. Specifically, it is a percent that it is the percent of money based on, like, if 100% is the money that you start with, this percent is the money that you will end with. So let's say this comes out to 150. That means you've gained 50% of your money over T years at this interest rate. So P is just being multiplied by a percent. When you realize that this number is a percent, it suddenly makes the rest of it make a little bit more sense, because what you look at is it's actually a couple percents multiplied together, right? Like this 1 plus R over N is also a percent. And this NT is how many times you're multiplying by that percent, right? So let's break it down and look at what the percent is first, and then why we multiply it by itself NT times. So the 1 here represents 100%, right? The number 1 is the same as the number 100%. So R over N must be an extra bit of percent of money that you're getting added on. And in fact it is. R, remember, is the percentage of interest that you get per year. And N is the number of times that they calculate it every year. And so let's say N is 4, right? So every quarter of a year, they add a little bit of interest to the account. So if they say that your interest rate R is 10% or 0.1, what they're actually going to do is not give you 10% every season, every quarter. They're going to, every quarter, add a quarter of 10% or 2.5% of whatever money you have onto your money. And by the end of the year, they'll have added 2.5% 4 times, which is the same as if they added 10%. Almost. It gets a little bit complicated because the second time they compound it, they're adding 2.5% of what you had at the beginning plus the little 2.5% they gave you earlier on. So it's actually better for you that they do it 4 times a year compared to doing it 1 time a year, because you just get a tiny little bonus. So in general, that's also true, by the way. The higher N is, even if everything else stays the same, if N increases, then the amount of money you get at the end, A, will also increase slightly. So the higher N is, all else being equal, the better things are for you, because that means that they're going to give you interest on top of the interest they already paid you throughout the year. So again, this 1 plus R over N is just them saying, okay, your interest rate is 10%, but we're going to calculate it 4 times this year, so we're actually just going to give you 2.5% each time we compound interest. So you can think of what's in this parenthesis as how much they're adding on each, or how much they're multiplying by each time they compound the interest. Now that makes this make a little bit more sense. NT, that's the number of times they compound per year times the number of years that you're waiting, right? That means this number is just the number of times total they're compounding interest. So basically, each time they calculate your interest, they're going to multiply by 1 plus R over N. And the to the NT power part is just telling you, okay, well, if they're compounding 5 times a year for 3 years, that means they're going to be compounding interest 15 times, right? So I would raise 1 plus R over N to the 15th power. I know that was a lot. Again, feel free to zoom the video back or come to me with questions if you have them. There are other resources online to explain why the compound interest formula is what it is. I highly recommend you understand them, because I'm fairly certain that I will not be allowed to give you the compound interest formula on your next test. You will be expected to know it. I'll double check on that, but assume for the time being that you will be expected to know this formula. This does not mean that I want you to memorize, it means I want you to understand it so that you can remember it. So if any part of what I said did not make sense, please make sure that you do some more research on your own or come to me until it does. Now, we can flip back over to our problem, where they said Mary invested $1,000 in an account with an annual interest rate of 8%. Again, annual interest rate is exactly R, right? So we already know, before we do anything else in this problem, I can already tell myself R equals 0.08, right? Because that's 8% written as a decimal. We just divide 8 by 100. How much will be in the account after 1 year? Okay, that's already more information. T equals 1 year. If the money was compounded quarterly, monthly, daily, and continuously. Now here's where these problems confuse people. They are asking you to calculate 4 separate things. they're saying how much if it was compounded quarterly, this is where n equals 4, how much if it was compounded monthly, which is n equals 12, how much if it was compounded daily, which is n equals 365, and how much if it was compounded continuously, which we'll talk about in a moment because it uses that other formula I haven't given you yet. So they're asking you to calculate 4 numbers. They're all going to be the amount of money in the account after 1 year, but they're going to be the amount of money in the account after 1 year if Mary invests in an account that compounds interest quarterly, monthly, or daily, or continuously, which are 4 different options you might see when investing in an account. And again, all these accounts have the same interest rate of 8% per year, so it might seem like you should have the same amount of money in any case, but it turns out that that's not quite true, which is in fact what the mathematician I was mentioning earlier noticed as they were doing their calculations, and it's what led to this last continuously thing. Let's calculate the first 3 first, and then we'll talk about the continuous one. So, the first thing we're going to do is quarterly. So I'll mark this in a color, and we'll work in that color. I can zoom us in a little bit at this point. So again, we know that the rate is 0.08. We know that the time is 1 year, and in this case, n equals 4. Right? We're doing quarterly over here. Quarterly means n equals 4. That's the number of times per year they're going to calculate that interest. So again, that means that every time they compound this interest, they're not actually going to give you 8% more of your money. They're going to give you 8 over 4%, so 2% more of your money each time. So our formula will look like A equals the principal, which we know, oh, by the way, P is $1,000 because our principal is 1,000. And they're asking us for A, right? They're asking us for the accumulated amount over time. I'm going to go a little bit darker on the screen. It's a little eye-searing. So A equals 1,000 times 1 plus R is 0.08, N is 4 to the 4 times 1 power. Again, I'm just plugging in from our formula. This was R up here, this was N, this was N, and this was T, which is 1,000 times, this comes out to 1.02, right? Because 0.08 divided by 4 is 0.02. And this is just 4. So at this point, it's very easy to just take a calculator and calculate what this is. I just pull up Google and I go 1,000 times 1.02 to the 4th power. It tells me that that is $1,082.43 approximately. It's a money problem, so we can round to the nearest cent. So $1,082.43. I'll put my little dollar sign there. Remember to include your units. So this is the quarterly scenario. But that's only one possible scenario. They asked us for quarterly, monthly, daily, and continuously. Since I'm working in different colors, I'm not going to label that this is quarterly, but it would be important in a real problem to label quarterly there. Now, monthly we can do in blue. We're going to do the same idea. So monthly, the only thing that changes here is n, the value of n. N is now 12 because we're compounding 12 times per year. So we still have our final accumulated amount is equal to our principal of 1,000 times 100% plus 0.08 divided by 12% now to the power of 12 times the 1 year. 0.08 divided by 12, what's that? That's like 4 over, or sorry, that's words. That's like 2/3 of a percent there. And so we're going to have, well, I'll write it out as 1.006 repeating, because that's 6. This bar over here just means it's like 6, 6, 6, 6, 6, 6, 6, 6. And that's going to be raised to the power of 12. If you don't want to type in this, which you shouldn't type that into a calculator, what we can do is actually just keep that as 0.8008 over 12. So if you look over here, I can go 1 plus 0.08 over 12. Order of operations says I don't need a special set of parentheses there because the multiplication and division happen before this addition, but if you want to be extra careful, you can put a set of parentheses in here. And then I'm going to go again to the power of 12 this time. Again, order of operations says that this 1,000 is not going to get raised to that 12th power because we're going to evaluate this first. But if you're scared, you can always put parentheses. And notice this gives me a very similar amount to what I had last time, but it's a little bit higher. It's $1,082.99.9. So we can round that up to $1,083.00. I'll say it's approximately equal to $1,083.00. So again, notice that that's it's only about 57 cents more than if we compounded monthly, but it is, or than if we compounded quarterly, but it is a little bit more. Daily, we can do the same trick. So we go, we'll do orange for daily. So for daily, n is 365 and nothing else changes. So our final amount will equal our initial amount, our principal of 1,000, times 1 plus 0.08 over 365 to the 365 times 1 power. So again, when we go back to our calculator here, it's now very easy to change these numbers. I just have to change all the 12s to 365s. And what we find out is that daily compounding also gives a little bit more money. Here it's about $1,083.28, because we're going to round up there. So I'll say that's approximately equal to, this like wavy equal sign means approximately equal to $1,083.28. So as you can tell, this R over N trick, where you can compound more times per year, it does give you more money. It is a very tiny amount more money, and thus it's pretty close, at least in the short term like this. Over the course of a long investment, it might actually be fairly noticeable, the difference. But one mathematician was asking, okay, but like, what if we compounded all the time, like even faster than daily, like minutely, like secondly, like millisecondly? What if we compounded 1 billion times per year, or 1 billion times per year? How would that affect the interest? And so this mathematician started calculating that, right? They started calculating. Actually, I can pull up Desmos and give an example here using these numbers. Let's. So here, let's say we have 1,000. Again, we're going to use the same numbers from the problem. 1 plus 0.08 over 1 to the 1 power, right? So this is if you compounded annually. And I'm sorry, actually no, I don't want to do 1 to the 1 power. What do I want to do here? 1 to the 1x power. So here I'm going to make my x value my time axis. So you can ignore what happens on the left there, because this doesn't make sense, because this is like at negative time if I'm saying x is my time value. But if I just change my scale a little bit here, so now you can see that she starts off investing $1,000, and after 10 years, she's made about $21,000. Sorry, $2,100. So she's added about about $1,100. At 20 years, she's at about $4,500 at 30 years. She's made it to $10,000, which is incredible. This is why investing young is sometimes good for people. But now what if I take this same thing? So this is where n equals 1, right? That's where that 1 and that 1 are coming from. What if I say now that we're compounding quarterly, so n is 4? Notice the curve is very close. In fact, for the first 10 years or so, they look almost like the same graph. They're only different by a little bit of money. Here, this is at 8. This is at 1850, and this one is at, the blue one is at 1884. So it's a difference of about $44 after 8 years, right? A very small difference. But you can see that they are diverging from each other, right? Well, let's keep trying to go even faster. Let's change n to be higher. What if we do monthly? Well, that's even slightly higher than the blue curve, right? And so it does look like as n is increasing here, what if we did daily? 365, this is 365. Again, the purple curve, if you zoom in, is ever so slightly higher than the green curve at every point. And so, a long time ago, a mathematician was like, okay, is there a highest curve? Because it seems like it's slowing down this benefit, right? The jump from red to blue is really big. The jump from blue to green is pretty small. The jump from green to purple is even smaller, even though purple is huge. Like, 365 is so much more than 12, right? And it turns out that there is a highest that it can go. Like I can do another one here where I do like 100,000, 1,000,000,000, and this one is 1,000,000,000, and you can see I still have to zoom in really far to see any difference between that and the purple one, right? And so this mathematician was curious as to, well, is there a highest curve? Because it looks like they're getting closer to another curve. And they use a trick called limits to calculate that, yes, there is one, and it looks like this. 1,000 times e, which we'll talk about in a moment, to the power of 0.08 times x. In this case, x being time, right? That makes this... Oh, wait, give me a second. Did I do something wrong here? Is this... Oh no, the lower one is red and this upper one is red too. I'm just going to hide this lower one. So notice this red curve is even slightly above, if we zoom in really far, it's going to even slightly be above that black curve. Oh my goodness, you can't even see it. We have to zoom in really close. But you can see the red curve is even slightly above the black curve, right? And what it turns out is this mathematician calculated that this red curve here, 1000e to the 0.08x, is what's called the limit of these other curves. That is, as n gets close, as n gets arbitrarily big, these other curves will get arbitrarily close to this one. And this was actually the discovery of the number e. The number e, like I said here, this was discovered, of course, by, popularized, the letter E, as its name, was popularized by Leonard Euler, who is the reason that everything in our math classes looks the way it does. But the idea is that, Bernoulli was the one. I couldn't quite remember the name. The idea is that as these exponential functions, as you increased n in these exponential functions, they approach this other function whose base was e. Notice that this is also very clearly an exponential function itself, right? Now, going back to our actual work, that gives us a new formula. Essentially, the limit of this as n approaches infinity gives us a new, slightly different formula, and you should pay close attention to how it's different. It's not just that there's an e in it. Some other things get moved around. So, our new formula is a equals the principal still times e to the rate times the time. Notice that n is nowhere to be found anymore because n is not a relevant thing to continuously compounded interest. The idea of continuously compounded interest is we're imagining n to be the biggest number it possibly can be. Effectively, you're imagining n to be infinity. So you're compounding interest at every moment of every millisecond of every day. And it turns out that there is an amount of interest that you would get from doing that we can calculate because of that limit trick. And it's exactly equal to this formula. It's a nice, much simpler formula. Again, the only thing that's in this formula that isn't in the original is called E, which is a number that is approximately equal to 2.71. There is a button for it on most calculators. You should be able to find it if you look. Sometimes it's like if you do second pi, it'll give you E, because pi and E are two really important irrational numbers, so they often get lumped together. So just like how pi is approximately 3.14, but it's not actually that. It's a little bit different because it has it has the extra infinite decimal bit going on. E similarly has a longer infinite decimal expansion, but we engineers or whatever would use 2.71 at least, unless they were dealing with numbers that need to be super, super precise, in which case they'd use a better estimate. But E is a real number. It fits on the number line, just like pi does, and it's sometimes called the natural number or the natural base. And we're going to see it more in a little bit when we talk about logarithms. So, again, going back to this problem here, they want us to know what happens if it's compounded continuously. And so, we're going to use our continuously compounded interest formula, which, as I just said, is A equals 1,000 times E to the 0.08 times 1. That's the rate times the time. So that's 1,000 E to the 0.08 power, which if I go back to my calculator here, I can get rid of all this funniness and go E to the 0.08. It thinks it's an address. And there we have $1,083.29 after rounding. That's right, continuously increased from daily by 1 cent. Or I'll say approximately equal to again. I keep doing this regular equal sign and then drawing the approximately equal over it. Usually you just do this. $1,083.29. And so what you should notice is that the more often you compound interest, the more interest you'll get, holding everything else like the rate and the amount of time equal and the principal equal. But you'll never get quite as much as if you compound continuously, which is what Bernoulli proved there. And so this continuously compounded interest, like if you have all things equal, if you have the opportunity to get the same bank account, the same rate, the same benefits, but one of them compounds interest continuously, you want that one. And otherwise, if they don't have continuous, you want the most compounding per year possible. So again, we have our 4 answers. This one is quarterly for $1,082.43, then monthly is $1,083, daily is $1,083.28, and continuously is $1,083.29. Now, the nice thing about this last formula that we did, A equals P times E to the RT, which sometimes people just say the word PERT because it kind of spells out the word PERT, is that it doesn't just apply to interest. It turns out that this number that Bernoulli found was so important to how exponential relationships work in the world that it just is, it applies to a whole bunch of other things. One of those is something called radioactive decay. So radioactive substances have this really interesting property where they, over time, they stop becoming radioactive because they release the particles. Radioactivity means that you periodically release particles that go flying off somewhere and might, cause health problems for people if they hit their important organs and stuff. But because you're literally releasing particles, you run out of them after a while. And so radioactive compounds eventually decay into either less radioactive or non-radioactive compounds over some amount of time. The rate at which they do that tends to be constant depending on the exact material, the exact radioactive material that you're talking about. And so they happen to know, for example, this thing called radon 222, that's, I think, radon with a molecular weight of 222, I could be wrong about that, decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay in 3 days? So here we can use a modified, or we can modify our PERT formula slightly. Instead of time being in years here, we'll assume that that's in days, but that's okay because our rate is also a daily rate rather than a yearly rate, so we don't have to do any time conversions, right? As long as R and T agree in terms of what the unit of time is, you don't need to mess with anything, if that makes sense. So here, R equals 0.173, T equals 3, and again, this is a daily rate, and this is a time in days. If you ever have something like a weekly rate and a time in days, then you should multiply that time in days by, or you should divide that time in days by 7, or multiply that rate by 7, just so that, or actually don't multiply the rate, divide the time in days by 7, just so that they match up. You don't want to ever have different units of time in your rate and in your time variable. Here, we can do the same thing. A, the accumulated amount, or the final amount, though notice how this is going to be less than our principal amount, equals 100, that's our principal, 100 milligrams of radon 222, times E to the, and now, sorry, I should say, it decays at a continuous rate of 0.173 per day, so we would actually make that a minus 0.173. Times T, which is 3. So if I again go to my calculator here, I go 100 times E to the negative 0.173. And I'm going to actually just do in parentheses here, I'm going to do the exponent in parentheses so I can do the times 3 as well. We get about 59.5 milligrams. They don't actually say to round your answer, which is a little bit silly. But if they say to round your answer, round it to that spot. If they don't, you can actually just give me the expression that you would have put into the calculator. Like, this would be the correct answer, if that makes sense, if they don't say to round. Because rounding will give you an approximate answer. This expression is the exact amount of radon 222 that will be left in 3 days. They also aren't very clear as to whether they want your answer here to be the amount that is decreased or the amount that is left. I would accept the amount that is left or the amount that is decreased in sort of a vague wording problem like this. Finally, they want us to graph some functions, identify their domain, range, intercepts, and asymptotes. So here, 2 to the x. Again, you can think about this by doing a table of values, right? What's x? What's 2 to the x? Well, if x is 0, then 2 to the x is going to be, or I'll say, if x is 0, 2 to the x is 1, right? Because 2 to the 0 is 1. If x is negative 1, this is 1/2. If it's negative 2, it's 1/4. If it's 1, it's 2. If x is 2, then 2 to the 2 is 4. And so you can get these points, which would look something like this. And you could connect them up, and you would start having a good idea of what the function looks like. And indeed, it continues doing what it appears to be doing in both directions. So here it continues approaching 0. It's got this horizontal asymptote at y equals 0. And here it goes up and to the right forever. It does not have a vertical asymptote here. Our domain is all real numbers, because every exponential has that as its domain. Our range, because notice here our a value, the number that was in front, is just a 1, right, because there's nothing written there. So that's positive, which means our range is from 0 to positive infinity, not including 0. It's this intercept here, this y-intercept, is at 0, 1, because that's this point, right? When you plug in 0, you get 1. And there is no x-intercept, so we would just call this the y-intercept. And then asymptotes, it has a horizontal asymptote at y equals 0. It has no vertical asymptotes. Over here, 3 to the negative x is a little bit interesting. This negative in front of the x means that when we do our table of values, plugging in 0 will still give me 1, but plugging in negative 1, that's like 3 to the negative 1, or 3 to the 1, so that's 3. If I plug in negative 2, that's 3 to the negative 2, or 3 squared, that's 9. If I plug in positive 1, that's 3 to the negative 1, which is 1/3. And if I plug in positive 2, I get 1/9. So what you're seeing here is I've flipped my values left to right from what they normally would be in 3 to the x. And so my function is going to look like this. It's going to kind of look like the horizontal reflection of 2 to the x. Though, if you look at each point, it's not the same point as 2 to the x because we're doing powers of 3 rather than powers of 2. So like here we would have negative 1 comma 3. Over here we would have like negative 2 comma 9 and so on. This would be 1/3. Again, our y-intercept is 1, and our domain is still all real numbers. Our range is still 0 to infinity. Flipping horizontally doesn't change your range. We still have a horizontal asymptote at y equals 0, and we still have no vertical asymptotes. Over here, 2 to the x minus 1 power plus 3, so this is the transformation. 2 to the x minus 1 plus 3. So this is like 2 to the x, which normally would just look like this. But the minus 1 on the x is a horizontal translation to the left, and the plus 3 is a vertical translation up. And so our point here that would normally be at 0, 1 is going to now be shifted, right 1 unit and up 3 units. So we have a point here at 1, 4, and the function's normal horizontal asymptote at 0 has shifted up by 3 as well. This is at 3. And so the function will approach y equals 3, but never quite reach it, and it will still go up and to the right there. And finally, this is just another set of transformations. I'm going to give this one without comment. So 3 to the x would normally be this. So negative 3 to the x would normally be that. And then minus 5 just means we shift it down 5 units. So this is y equals 5 over here. It goes like this. This would be the point 0, -6. Again, play around in the graphing calculator and do some calculations, do some tables of values, and you'll see why these functions show up the way they do. So it's been a little over an hour, and we've just gotten to the end of exponentials, so I'm going to start a separate video for logarithms.